So, in sound-based distance sensing, we have some sort of transmitter. Uh, Actually, let's put the transmitter here. This is our transmitter, TX, and we're going to have our receiver over here, RX. And they're going to be separated by some sort of distance. Let's just, for our example, let's just call this distance 2 centimeters or 0.02 meters. So they're pretty close together. And what's going to happen is that sound is going to uh, come out of the transmitter, bounce off an object, and come back to the receiver. And we're going to measure the amount of time it takes for that sound to go from here to here. And what we're really looking for is this kind of center distance here. We'll call that D. That's what we're really looking for. But we're measuring a time, right? We're measuring the amount of time it takes for the sound to come out of here and reflect back to the receiver. So there's a couple things that we need to know, right? We need to know that the velocity of sound, right? Speed of sound is 340.29 meters per second. And we need to know what time we measured, right? That's what your device is going to get, a time that was measured, or pulse length. So here we've got, for this example, we'll say we've got 0.02 seconds, just to keep it simple. They put a space there, so it's a little. There we go. So the first thing we need to do is take this data and get a distance from it, right? We need to go figure out what the distance is, right? If you've got a speed and you've got a time, you can figure out what the distance is. So, and we'll call this distance the sound is traveled. Now here's the thing. We actually have two triangles here, right? We've got the distance there and then the distance back. And we can just work with just this one right triangle because it's easier to work with right triangles. So really we can just take our time and divide it by 2, right? Our time divided by 2 is going to give us this length here. So just that's a kind of step I kind of do in my head there, right? But it's a critical thing, right? So we're going to take 340.29 meters per second. And I guess just for the sake of clarity, right, we're going to multiply it by 0.02 seconds divided by 2. I'll just put that in there just so we have it. And so we work that out, and it comes out to be 3.4029 meters, right? That's how far, that's this distance right here. And now I always like to just draw my triangle out, even though we already drew it. I'm going to draw it again. We're looking for D. We know that this distance, right, so we've got two triangles here, so we need to take this distance and divide it by 2. So that's really 1 centimeter between the center point and the transceiver. So that's 0.01. And we know that this is 3.4029 meters. So now it's just an a squared plus b squared equals c squared situation. So we can write that out, right? 3.4029 squared equals, oops, daisies. That's equals 0.01 squared plus our distance here that we're trying to get, which is d squared. And, right, we do some mathemagic on that, and we're going to find that d equals, drumroll please, 3.4028. Now, does this number look familiar? Well, it's pretty similar to this number right here. And why is that? Well, if you think about it, sometimes when your triangles, your sketches can be a little misleading, because what that triangle really looks like, right? You've got this little 2 centimeter line, or I guess in our case for our triangle, it's a 1 centimeter line, and then you've got this massive length of 3.4 meters. So, sorry, it's not a very good representation. It's a really narrow triangle where we can say that this distance is pretty much approximately the same as that distance. And so that can be a fair approximation if you're trying to minimize computations, right? You don't want to have to go through all this stuff. This is a pretty easy and straightforward computation that you could do. But I guess it's just depending on what your instructor might be asking you for. Maybe this precision is, important to them.